Hello, this is the Unit 6 practice exam. So there are a lot of concepts involved on this exam, but it's not inclusive of everything that will be on the actual exam. So make sure that you take a look through your notes, look through the review sheet and the concept summary, and make sure that you just have a good idea of most of the things that come out through this unit, because there could be concepts that are on the actual exam that are not presented here, but this should give you a general idea of how well you would do. Okay, so this first one, it says, if you mix two nonmetals, what type of bond will you most likely get? Two nonmetals makes a covalent bond. If you have a metal and a nonmetal, that is an ionic bond. Two metals make a metallic bond, but that is not something that we talked about, so you're not responsible for that. In a covalent bond, electrons are shared. In an ionic bond, they are transferred, split, and destroyed, or just decoy answers. Which of the following substances are known to make crystalline lattice structures? This is one of the properties of ionic compounds. So we went through a list of ionic compounds in its chemical bond notes. So make sure that you look through that set of bonding notes and figure out, there are something like 5 or 6 different properties of ionic substances that you have to know. Speaking of which, number 4 says, which of the following is not a property of an ionic substance? The answer here is that they have low melting points. They have high melting points, all right? So the rest of these things are true for ionic compounds. Ionic compounds do conduct electricity when they dissolve in water. Also, they dissolve in water mostly. They're brittle, all right? And they involve a metal and a nonmetal. Number 5, it says true or false. It is possible for a molecule to be polar even if it has nonpolar bonds. All right, so for this one, what we're looking at is some of these shapes that end up being polar no matter what. So for instance, there's the bent and the trigonal pyramidal shapes. Those ones are always polar. So even if they have nonpolar bonds, they end up being polar because of the weird collection of electrons that happens around them. So this one here is actually true. The converse is also true. If there's polar bonds, it's possible for it to be nonpolar overall if it's a symmetrical structure. So if it has polar bonds, but it's tetrahedral, linear, or trigonal planar, and it has the same atom all the way around so that it's symmetrical, then it can end up being nonpolar even if it has polar bonds. So both of those things are true. Okay, it says using the rule of thumb, which type of bond would most likely occur between sulfur and nitrogen? Those are both nonmetals, all right, which means that a covalent bond would occur. Next one here, phosphorus and iron have electronegativities of 2.2 and 1.8 respectively. Specifically, what sort of bond would be formed? All right, so for this one, the difference there is 0.4. 0.4 is on the range of polar covalent. All right, if it's 0.3 or less, it's going to be nonpolar covalent. If it's above 2, it's going to be ionic. So generally speaking, there, just know those general ranges so that you can answer that sort of question. It says the dipole moments in a linear molecule are shown here to the right. All right, so we've got these vectors here that are pointing off to the right. What these show is the arrowhead points the direction that the electrons are moving. The plus sign is to show that that part of the molecule is left more positive. And so if you can see here in this A to B to C molecule, what's happening here is that electrons are generally moving off to the right. Okay? If that's the case, then there is an uneven distribution of the electrons, which is the definition of something that is polar. All right? This would likely have a partial positive charge on this end of the molecule and a partially negative charge on this end of the molecule because the electrons are moving over there to the right. All right, so in regard to the same molecule from question 8, where would the greatest electron density be, or what atom would have the greatest electron density? It's C, because that's the direction that the electrons are moving in. Number 10, hexane is a colorless nonpolar liquid at room temperature. Knowing this, it would most likely mix well with. Okay, so if it's nonpolar, it's going to mix with other nonpolar things. All right, so it would mix with oil, because oil is nonpolar. Water is polar. I expect you to know that about oil and water, so make sure that that's something that you know. All right, the next 3 problems here are all about constructing Lewis structures. I'll kind of lead you through the process of elimination here. So This first one is cesium nitride, CS3N. So in this one, it's an ionic bond because I've told you use the rule of thumb to try and determine between its ionic or covalent. So it's a metal and a non-metal, which means it's going to be ionic, which means that some atoms are going to be giving their electrons to other atoms. In this case, the cesium, being the metal having the lower electronegativity, is going to give its electrons to the nitrogen. Cesium has 1 electron each. All right, so each one of the cesiums loses 1 electron. Nitrogen has 5 electrons. It's going to gain 3. All right, and so you have to look around at these and figure out which one makes the most sense. All right, in this case, it's B. A and C are both covalent structures, so those don't make sense at all. And then the charges are wrong for D. The charges are backwards on D. So B would be the correct answer. For this next one, SO3 2-, we have to think about the octet minus the valence plus the charge and divide it by 2 and get the number of bonds and then make the structure that way. So we've got S, which has 6 valence electrons, and then so for our valence electrons, that equals 6 plus, there's 3 oxygens. Those each have 6 actually as well, so that ends up being 24. All right, so that's for the valence. For the octets, there's 4 atoms that are all of them non-hydrogen, so they all want 8. So 32, and then you do 32 minus 24 plus the charge plus -2, all divided by 2, and you get here that there are 3 bonds in this one. Okay, so the general rule is that you put S in the middle, and there are 3 bonds, and so like this one doesn't make sense because it's got 4 bonds. This one also is out because it has 4 bonds. Then the next thing you have to do is you have to, after you put it in 3 bonds, you have to make sure that everything has octets around it. So this molecule here is messed up because that only has 6 electrons around it. So does this and this. Actually, everything only has 6 around it. So this one's out because those don't have octets. All right, and so this one here, everything, if you count the electrons from the bonds and the electron pairs, everything ends up having octets there. So that works out. pH3, so for this one, it's a covalent structure. By the way, I should mention on this last one, the way that we knew that we were doing that octet minus the valence plus the charge is because it was a polyatomic ion. We had that charge up there, so that clues you in that it's going to be one of those ones there. All right, back to 13. So on this one, it's a covalent structure because phosphorus and hydrogen are both nonmetals, so it's going to form covalent. So there are 2 here that are ionic Lewis structures, this one and this one, we're going to throw out. Okay, and so we're looking at these 2 possible covalent structures. If you're especially savvy, you might realize that those hydrogens look really weird, like you're not going to have hydrogens with electrons all around them because hydrogens only want duets, all right? They don't want the octets because they want to be like helium. But even if you didn't, you can go through and just make the Lewis structure the old-fashioned way. Hydrogen has 1 valence electron. Phosphorus has 5. We put the hydrogens all around the phosphorus. Circle these here. All right, and we end up getting one that looks like A. So that is how that one goes. Okay, for section D, we are just going through looking at these structures and figuring out what shape they are, what their bond angles are, and what the polarity is. And so what we have to do is we have to look at the central atom. So S is the central atom here. It has on it 4 domains. It has 2 bonds, 2 single bonds, and 2 electron pairs. All right, and so if you look at your chart and you see 4 domains, 2 of them are bonding domains, 2 of them electron pairs, you should get that the shape is bent. All right, the bond angles for this particular bent are 104.5. All right, and the polarity, this one, if it's bent, all bents and trigonal pyramidals are polar automatically. Bents and trigonal pyramidals are polar. So, All right, for HCl. This one, the shape is kind of funny. It's got just 2 atoms in it, so we call it linear, but it's a diatomic linear, which is a little bit funny. Diatomic linear. All right, the bond angles on this one, there are no bond angles. All right, and polarity, so it's a linear structure. So if it's symmetrical, it would be nonpolar, but if it's asymmetrical, it's going to end up being polar. You can see this one actually is asymmetrical because it's got a hydrogen on one side and a chlorine on the other side. If it was diatomic like this, the only things that end up being nonpolar are like H2, which has 2 H's, or Cl2, which has 2 Cl's. All right. So this one's polar because chlorine is more electronegative than hydrogen is, so the electrons are going to move there toward the chlorine, right? And we're going to get a negative charge on that side, so this one is polar as well. CO2 here is linear. We know that because if you look at the carbon, okay, because we're only looking at the central atom, count the electron domains, it has 2 domains on it. It's got a double bond on the left and a double bond on the right. All right, none of those are electron pairs, so it's two total domains, 2 bonding domains, 0 electron pairs. Okay, so the shape there is linear. This one has bond angles of 180 degrees. All right, and linear is a symmetrical structure, so you look and check and see if this one is going to turn out to be symmetrical. If you look here, we've got an oxygen on the left, we've got an oxygen on the right. It ends up being symmetrical. Really, if it's one of the symmetrical structures, which include tetrahedral, trigonal planar, and linear, if it's one of those 3 structures, tetrahedral, linear, or trigonal planar, and it has the same atom all the way around it, like in this case it has oxygens on the outside, it's going to be nonpolar, all right, because that indicates that it has symmetry. So this one ends up being nonpolar. Of course, if you were filling out the exam, you would be using the corresponding letters here to identify each of those shapes and bond angles and polarities. But this should just give you an idea of how things go with those. So if you're confused by any of these concepts here, make sure that you watch the video for the Unit 6 review. And also, I'm open if you have any questions, you can come in and ask.